Okay, in the last lecture, we discussed the wave function for a hydrogen atom. So it looks like some normalization constant and the polynomial and exponential term giving and some Laguerre function, something like this, and the argument is 2r over Na0. So here n and l are quantum numbers introduced while we are trying to solve the partial differential equation. And there are some restrictions on these quantum numbers. So n could be some positive integer number. And even though we haven't discussed the restriction on L, but L should be the number integer between 0 and n. So from 0 to n minus 1. Integer number. So let's discuss the restriction on here. So why is there a maximum bound for quantum number L? So in the last lecture, we discussed the presence of the Laguerre function. In the hydrogen atom's radial function. And the subscript here, n minus L minus 1. This is the order of the Laguerre polynomial. So that means n minus L minus 1 could not be no less than 0. So if it is less than 0, the polynomials could not exist, and we just have the 0 number. So there is physically no meaningful solution for radial function. So it doesn't make sense. So n minus L minus 1 should always greater or equal to 0. So that's why we have such maximum bound for the quantum number L. So quantum number L could not be greater than n minus 1. So this will complete the restrictions on quantum numbers. So in the previous lecture, like 2 or 3 previous lectures, we discussed the quantum number restriction for m. So m could be 1, 0 plus minus 1 plus minus 2n plus minus l. So all these quantum numbers are derived from why we're trying to solve the partial differential equation for describing the wave function for specific problems. So it is not derived or it is not set arbitrarily. Okay. And I want to mention the normalization condition. Normalization. So R and L. So we are going to put two indices n and L for radial function because these are two quantum numbers required to specifying the radial function. So if you want to check the normalization condition for the radial function, then you have to integrate from 0 to infinity dr. And we need to introduce r square because of the using spherical coordinates. So infinitesimal volume element is 4 pi r square, but we are now focusing on the radial part, so we don't need the 4 pi. So we just used r square as the volume element. And the other things are quite similar. So you are going to take the complex conjugate and you're going to multiply the original function. And that should be 1. Okay, and let's discuss the number of nodes in the radial part. So we have specified the function form of the radial function, and you can take a look at each term in the radial function. So let's rewrite here. So when we say the node in chemistry, it means the point where the function becomes 0, right? So you can take a look at which function could be 0 for this function, r to l. Does this function become 0 for the range of r from r 0 to infinity? This is actually just the increasing function, right? From 0 to infinity. So there is no 0 in between 0 and infinity, right? So there is no node for RL. And what about the exponential function? This is actually a decaying function, but exponential function can never be 0. Even though it is it approaches to 0 very fast, but it is still not 0, right? So there is no node here, and that means the only possibility for this function to be 0 is here, Laguerre function. And as I mentioned, the Laguerre function with these indices, this is n minus l minus 1 polynomial. So when I say the general n minus l minus l polynomial, it should have n minus l minus 1 roots, right? So if you think of the quadratic function x squared, something like ax squared bx plus c, then generally it has 2 roots, right? So the order of the polynomial means the number of roots. So we have m minus l minus 1 roots because of the Laguerre function. So number of nodes in the radial part is m minus l minus 1. So if you remember the number of the nodes in the angular part, number of nodes in the angular part, that would be L, right? So it is the sum of L minus absolute value M and M, right? This is from the theta and this is from P. So if you sum up these two numbers, that will give you the total number of nodes in the wave function. So that's why we have the m minus l nodes for the wave function with quantum number n. Okay. So I guess now you understand why 1s orbital doesn't have any node, and 2s has one radial node, and 0 angular node, something like this. So 2p has 1 radial node and 1 angular node. Oh, sorry, that should be 0, right? No radial node and 1 angular node. Okay, let's move on to the next page. So in this page, I want to discuss the good quantum numbers. So in science, good is quite vague meaning, but you will soon realize the meaning of the good here. So we have 3 quantum numbers so far. So n, l, and m. So I want to put the subscript L here to distinguish the M sub L from M sub S, which will be discussed later in this lecture, which is for spin quantum number. Anyway, this set of the quantum numbers makes the good quantum number set because we have 3 different operators. The Hamiltonian operator, H hat, and we have the total angular momentum operator, so L hat, and we have the G component of the angular momentum, so G component of angular momentum, Lg. So the wave function psi n l m sub l, this is the simultaneous eigenfunctions of these 3 operators, h hat, l square, and lg square. Right? So we have discussed that this is the wave function for Hamiltonian. We derived this wave function from the Schrödinger equation. And as you may remember, the Hamiltonian and the total angular momentum, they share the same eigenfunction, right? Because they are commute, right? Also, total angular momentum is commutable with the G component of the angular momentum. So from these 2 relations, we can say that Hamiltonian is commutable with G component of the angular momentum, right? So from this commutation, we can say that the wave function psi is a simultaneous eigenfunction of these 3 operators. So n is for the Hamiltonian, which determines the energies, and L is for the total angular momentum, and ML, this is the G component of angular momentum. So we can assign the physical meaning of these 3 quantum numbers, and the reason why I called these 3 quantum numbers are good quantum numbers because they are the wave function expressed with these 3 quantum numbers are simultaneous eigenfunction of these 3 operators. Okay, so this is the end of the section 7.1, and let's move on to section 7.2. So section 7.2 is about the s orbitals. S orbitals are spherically symmetric. So we all know that s orbital has the shape of the sphere, right? It looks something like this. So for the principal quantum number n, the energy of the hydrogen atom is expressed as En minus 4 pi epsilon 0 A0 n square and E square here. So as you can see here, at least for the hydrogen atom, energy is totally determined by the principal quantum number n. So that means energy of the 2s orbital of the hydrogen is exactly equal to the 2p orbital of the hydrogen atom. Even though for multi-electron atoms, these two orbitals have different energies due to electronic repulsion. But at least for hydrogen, we have this equality. And as you may very well know, the angular momentum quantum number L, so from 0 to n minus 1, this is the magnitude of the angular momentum, right? Because the L square has the eigenfunction of spherical harmonics, and its eigenvalue is given as h bar square L multiplied L plus 1. So this means the magnitude of the total angular momentum should be given as h square root of L plus 1. So according to the number of L, so we give the name for that orbiter. So L equals 0 is S orbiter. This is for sharp orbiter. N equals 1 is the principal orbiter. And L equals 2 is the diffuse orbiter. And L equals 3 is fundamental orbiter. And after that, we just following the alphabetical order. So F, G, H orbiter, and we don't really use the I orbiter. And the magnetic quantum number M sub L. So the eigenvalue of the LG operator M sub L H bar. So eigenvalue is ML H bar. So the role of the ML can be seen when you apply the external magnetic field. So actually we learned that 2p orbiter is threefold degenerate. So there are 2p plus 1, 2p 0, 2p minus 1. So the subscript means the magnetic quantum number. So without external magnetic field, they are threefold degenerate, but when you apply the magnetic field, they are split into 3 sub-level. So M equal to 0 does not really respond to the external magnetic field, so they remained on the same energy level. But M equal minus 1 and M equal plus 1 respond to the external magnetic field. And we see the energy decrease and energy increase depending on the magnetic quantum number. So we are going to discuss that one later when we talk about the Ch7 effect. Okay, so this is the brief discussion on the three quantum numbers. And let's write down the radial part of the 1s orbiter. So you can just look up some chemical textbook. So all you have to do is you have to find the wave function for n equal 1 and L equal to 0. And you will find that it is given as 2 over A0 3 to 2 exponential minus R over A0. So I might not mention the physical meaning of A0, so let's do that now. So A0 is the Bohr radius. So it is exactly the same value when Bohr tried to explain the line spectrum using his orbit model. Even though there is no orbit in nature, but his insight is quite impressive. And the A0 derived from the quantum mechanics is actually very equal to the Bohr's initial radius. So we give this constant. We give the name to this constant as the Bohr's radius. So you can play with this. So if you want to calculate the probability of finding in some specific region of 1s orbiter, then you can take the square of the 1s orbiter. So originally in quantum mechanics textbook, you always have to multiply the complex conjugate and itself. But we are now discussing the real wave function, right? So there is no imaginary part here. So basically taking the square is exactly equal to the multiplication of original function and its complex conjugate. So if you take the square of R1s, then it should 4 over A0 to 3 and exponential minus 2R over A0. But actually this is probability density, right? This is not strict probability. So that means if you want to calculate the probability, then you have to multiply the volume element, right? So volume element for the radial part in the spherical coordinate is r squared dr, right? So if you want to find the probability of finding electron between 0 to some specific value like A0, then you can integrate this probability from 0 to A0. Okay. And let's move on to angular parts of 1s orbiter. So angular parts depends on two variables, the theta and p. But we are discussing 1s orbiter, and for here L equal to 0 and ML also should be 0 due to the restriction on that quantum number. And if you're trying to find the spherical harmonics with L equals 0 and M sub L equal to 0, it is just a constant 1 over square root 4 pi. So that's why we don't see any angular dependence for 1s orbiter, right? There is no variable theta and p, so it is just a constant. Okay, so complete 1s wave function. Complete 1s wave function. So when we say the atomic wave function, you might just want to say 1s orbiter. So it has the exactly same meaning. So 1s wave function and 1s orbiter, it has exactly the same meaning. So if you want to write down the wave function for 1s orbiter, then this can be designated as psi 1s and r zeta and p. And the other way to label the 1s orbiter is to use the three quantum numbers. So psi n, so n should be 1, and l should be 0, and m sub l also should be 0. So psi 100 also indicates 1s orbiter. So according to the separation of variables, it should be the multiplication of two functions, the radial part and the spherical harmonics. And let's fill the indices. The radial parts require two quantum number, n and l. So it should be 1, 0 here. And for the spherical harmonics, it requires two quantum number, l and ml. So 0, 0 here. So in a shorthand, we might want to use the Dirac notation. So there is a vertical bar here, and 1, 0, 0. This is a cat vector for 1s orbiter. So in the undergraduate quantum chemistry course, we don't really use bracket notation, so it is just optional, okay? You don't really have to practice with this notation at this course. Okay. And there is some discussion related to 2s orbiter, but it is quite similar story, so you can just read your textbook. Okay, and we just check this part. So if you want to write down the wave function for 2s orbiter, then that should be 2, 0, 0. That means you need to find R20 and spherical harmonics of 0, 0. So you can easily figure out that 2s, any s orbiter should have the 0, 0 spherical harmonics. That means they don't have any angular dependency. So they all of them look like sphere. And you may want to calculate the average value of R. So in our quantum mechanics, there is no definite orbit, right? So the electron just move around of the nucleus. So we just imagine the electrons like cloud around the nucleus rather than a specific orbit. But still, even in this probabilistic picture, we can calculate many things like the average value of R or the maximum value of R, right? I mean, the maximum probability, the R for the probability maximum. So most probable point. So if you want to calculate the average value of R, then it is just calculating the expectation value for the wave function. So from 0 to infinity, you are going to integrate the volume element r square and psi 2s, and you are going to sandwich your operator between the complex conjugate and your original function. Actually here we also include the angular part, right? So that means we have to consider the angular part. So 2s orbital has the three independent variables r, theta, and p. So we have to integrate over the theta and p all together. So you can practice for this problem. Okay, let's move on to the next page. Section 7.3 is about the p orbital. So the title is there are three p orbitals for each value of the principal quantum number n equal or larger than 2. So when L is not equal to 0, so hydrogen atomic wave function or hydrogen atomic orbital are not spherically symmetric, which means they have now they have the dependence on theta and p. So we have the non-constant spherical harmonics. So we are going to concentrate on the angular part of the hydrogenic wave functions. So let's talk about the p orbitals. So p orbital has the quantum number L as 1, and this means m sub L should be -1 or 0 or +1. So there are three possible m sub L. So let's write down this pair, L equal 1 and m sub L equal to 0. So this one corresponds to the spherical harmonics of y10. And if you look up the table, then it is just so even though the constant looks a little bit messy, but it is just a cosine function. And let's look at the other two p functions. So m sub L equal to +1 and m sub L equal to -1. So they will have the spherical harmonics of y1 -1. So they look like some messy constant, normalization constant, and if you look up the table, you can find these two wave functions. So actually the number doesn't really matter here because they are just a normalization constant. So if you integrate the sine theta multiplied by exponential IP, then you can obtain that value, so it doesn't really matter. But the problem is we have the imaginary number here. So this means the orbiter corresponding to this spherical harmonics should be imaginary number, should have imaginary parts. So that function should be described on the complex plane, right? So 2p plus 1 or 2p minus 1 should be described on the complex plane, while 2p0, this is just a real number, right? So we can depict or we can graphically describe this orbiter 2p0 on the real plane, but we cannot do the same thing for this. So this is a little bit problem. This causes some problems because even though we can discuss many things in complex plane, but we cannot really observe the complex plane. We live in the real world, right? So that's the problem. But there is a nice trick that we can try to use. So Hamiltonian is the linear operator, right? So if y1 and y2 are the solution to Schrödinger equation with the same energy value, then the linear combination of these two numbers, these two functions, are also the solution to the Schrödinger equation with the same energies. So this means 2p plus 1 and 2p minus 1s are solution to the Schrödinger equation for hydrogen atom, right? And then, even though we have the imaginary part for 2p plus 1 and 2p minus 1, the linear combination of these two functions will have the same energy, and they are also the eigenfunction of the Schrödinger equation. So you can take the plus combination and minus combination to eliminate this imaginary part, right? This is simply the cosine p plus I sine p, right? So anyway, taking the linear combination will eliminate these two, and the final result looks like 2p orbiter So this is the minus combination, and it will gives you 3/4 pi square root. And the other function is the plus combination. So can you name these two p orbitals in real space? So let's take a look at this part. So cosine p and sine p. So in the spherical coordinates, the p is the angle in the xy plane, right? So when you project your vector or your wave function on the xy plane, then you will have the vector like this, and this is your p value. So cosine p means it is the projection on the x-axis. So that's why we label this orbiter as px. This orbiter is lined along the x-axis. And what about the sine p? Sine p is the projection on the y-axis. So this orbiter is labeled as py. So solving the Schrödinger equation for the hydrogen atom, especially for 2p orbiter, it does not really directly give the real orbital shape, but according to this linear combination, we are converting the complex wave function into real wave functions. That is the final result that you can see in your general chemistry textbook. Okay, so and there are some discussions on d orbitals in our textbook, but I think you can just take a look at, and we can move on to the next section. So section 7.4 is the energy levels of H atom are split by a magnetic field. So from here, we are going to take a look at the energy level very, very closely. So as you may know, 2p orbitals are threefold degenerate, but when we apply the magnetic field, this orbiter is actually split into 3 sublevels. And in the next session, we are going to introduce the spin. And the interaction between the orbiter and the spin will split this energy level further. So you will see the fine structure of your hydrogen atom. So that means we use the very, very poor microscope to observe the energy level. So we just see the single energy levels, but we have a much better microscope. So we can distinguish very closely spaced energy levels, and we can explain the physical meaning of that energy splitting. So we are going to take a look at closer and closer. So the energy difference becomes smaller and smaller. Okay. So first, let's discuss Ch7 effect. Ch7 effect is basically can be illustrated with this one. So nothing is really difficult, but we are going to derive the amount of energy stabilization and destabilization. Okay. So let's assume that there is a electric charge around a closed loop, and the magnetic dipole M caused by the motion of electric charge around the closed loop is M equal IA. So here I is not imaginary number. This is the currents in amplitude, and A is the area of the loop. So this is given in square meter. And the current I, this can be calculated by the charge Q multiplied by the velocity divided by 2 pi r. So this is the parameter of that circle. So r is the radius of that circle. R is radius, and Q is the amount of charge, and B is the velocity. So if you plug the current value in this equation, magnetic dipole will have the QRV divided by 2. But if you want to generalize this expression for any cases, not just for the circular orbit, so we are going to introduce the vector quantity, magnetic dipole m bold. So bold is for the vector quantity. QR V divided by 2. So I guess let's put arrow on the label to indicate that that quantity is the vector rather than a bold. Okay. So using the fact that angular momentum is given as the r cross p and linear momentum p is m multiplied by vector b. So we can replace r cross v with L and mass m, right? So r cross v should be equal to L divided by m, right? So instead of r cross b, we are going to use L over m. So that will give you the magnetic dipole Q divided by 2m and L. So for electron, so we are discussing on hydrogen atom, and there is a charge there is only one particle that moving around, so that is the electron. So the charge Q, that should be the charge of an electron, right? So Q should be the absolute value of the unit charge with minus sign. So for electron, so magnetic dipole is given as like this. Let's put E here to explicitly indicate that this is the mass of electron. And actually this is the dipole, magnetic dipole. Yeah, you should be very confused because there are two M here, but I cannot come up with better notation for this one. So this is mass, and this is magnetic dipole. Because we are trying to explain the impact of external magnetic field, that's why we are trying to derive the expression for magnetic dipole. Okay. So now we derive the expression for magnetic dipole caused by the circular motion of electron. So that is the important expression here. And we want to calculate the potential, its impact on our potential energy. So potential energy of magnetic dipole in external magnetic field B. So that is B is equal to minus M inner product with magnetic field B. So let's simplify the situation. So we just apply the magnetic field along the G direction. So magnetic field B has the only component K vector. So K vector is the unit vector along the G axis. So if you want to calculate the inner product of M magnetic dipole and the external magnetic field, then it is just the G component of the magnetic dipole multiplied by G component of the external magnetic field, because we don't have any I vector and J vector here. So I and J is the unit vector for X and Y axis. And we know the expression for magnetic dipole M, right? So if you introduce that result here, then the minus 2me. So now, rather than the total angular momentum, we are going to use the angular momentum along the G axis, because we are dealing with the mz. So Lg here, bz. So the potential energy stemming from the interaction between the magnetic dipole and external magnetic field is given as absolute unit charge magnetic field G component of the angular momentum to me. Okay, so we derive the energy for magnetic dipole interacting with the external magnetic field. And this is a physical quantity, right? Then that means we can come up with the operator corresponding to this physical quantity, right? So physical the operator that corresponds to this physical quantity is L, replaced by Lg operator, E, right? So now, let's write down the Hamiltonian. So Hamiltonian is consisting of two parts. So the first part is the H0. So it is just a simple summation of the kinetic energy and the potential energy, which means the potential electrostatic interaction energy between the electron and nucleus. And in addition to that, now we have the one extra term, E Bg divided by 2me Lg. Right? So the Schrödinger equation that you have to solve, H hat psi E psi. Now we have to use this one instead of H0. So your problem is H0 But fortunately, the hydrogen atom's wave functions, the hydrogen atom's orbiter, are eigenfunction of both H0 and Lg, right? So you remember that commutation, Hamiltonian, and total angular momentum square, and G component, all of them are 0, which means they share the eigenfunctions. So if we have to write down them separately, if you apply the just plain Hamiltonian consisting of two parts, the kinetic energy and the electrostatic, that will give you very well-known value, 8 epsilon 0 square h square n square and square. This one, which depends on the principal quantum number n. And we also know the eigenvalue when you apply the LG operator on psi, right? That is simply ML H bar psi. So this is your eigenvalue. So actually you don't need to solve the new Schrödinger equation in the presence of the magnetic field. You already have the wave function and you already know the eigenvalue. So simply you can just distribute this operator on the wave function. So your final result will be the total energy will be the summation of these two terms. So minus and 1 over n square plus, so there is a constant already here, E, so this is the energy levels of a hydrogen atom in the presence of the magnetic field. So now we have two quantum number dependency, n and m sub l. So n is 1, 2, 3, like positive integer, and m sub l, that should be something like this. So this will, the first term will determines the energy levels, like 2p orbital is here. So this is the y-axis is the energy axis. So 2p orbital is here. And due to the presence of the magnetic field, these three energy levels will split. Now you understand why ML equal to plus 1 goes up and M sub L equal to minus 1 goes down because of this term. So you have M sub L here. So M sub L equal to plus 1 will increase the energies, while the M sub L equal to minus 1 will decrease the energies. And there is no effect on M sub L equal to 0. And actually, you can calculate the energy spacing between these energy levels, right? Because this is simply the energy shift by simply this much. Unit charge multiplied by magnetic field divided by 2me multiplied by h bar. So example 7-5 actually calculate the energy difference energy difference between 1s orbital and 2p orbital and 2p0 and 2p plus 1. So let's erase this part and let's extend the energy scale, and 1s might be somewhere here. So we are not going to follow all the calculation procedure, but in a typical condition with 1 Tesla, this energy difference the energy transition between 1s and 2p orbital is about 1 10 to minus 18 joule. I just want to give some impression on a number scale. And this energy difference, due to the magnetic field, this is like 10 to minus 24 joule. So comparing to this main transition, the splitting by the external magnetic field is quite small, right? It's 10 to 6 times difference. So if you let's go back to the very first of this page. So if you have a very poor microscope, then you only see such large difference, 10 to minus 18 joule. So you cannot really see this small, tiny energy difference because you have poor microscope. And actually, when I say microscope, it's not really microscope. It's just like a analogy. Okay. So you can always measure the energy difference using spectrometer. So if you have a better and better spectrometer or microscope, then you can now distinguish such tiny, small energy difference. Then we will realize that, oh, there is sub-energy levels. So 2p energies are not really degenerate in the presence of the magnetic field. Okay, so that's how the science evolves from the beginning. Okay, let's move on to the next page. So section 7.5 is about the spin. The title is Electron has intrinsic spin angular momentum. So the electron has its own angular momentum and it is called spin. So it is not from the external effect. Okay? So spin, let's talk about the spin. There is a very interesting experiment, the Ch7 and Gelach. So they passed a beam of silver atoms. So please remember that the electronic configuration of the silver atom is like 4d10 and 5s1. So it has one electron. It has a single electron in the outermost electronic shell. And they pass through the silver beam to something looks like this. So there is magnetic field between here. So the reason why they have such such weird shape is they want to apply the inhomogeneous magnetic field. Because if you apply the homogeneous magnetic field, then you cannot really see the splitting of the energy levels. Okay, so and let's take a look at the final result. So silver beams pass through this area, and due to the inhomogeneous magnetic field, you can expect the splitting of that part. And let's talk about the final. Let's imagine the final result in terms of the classical mechanics. So what is the main difference between the classical mechanics and quantum mechanics? Energy discontinuous in energy, right? Quantization. So in classical mechanics, scientists think that the energies are continuous value. And even though they have some splitting, they expect something like some continuous like this. Continuous distribution. But actually this is not observed. This is not observed. So quantum mechanics, the classical mechanics is wrong for this one. And final result is you have very clear two spots, only two spots, according to quantum. So this is another evidence of the quantization. And here we are talking about the angular momentum. And as I mentioned, the angular momentum is 2L plus 1 degenerate, right? But here you see the twofold degeneracy. So this means 2L plus 1 should be equal to 2. Then from here, you might want to say L should be half the value. I mean 1 over 2. So we haven't seen the angular momentum of 1 over 2, right? At least for the orbiter. Orbiter has the integer number L. So L equals 0 is the S orbiter, L equals 1 is the P orbiter, but we have never seen L value equal to half integer. So people think that, so electron might have its own angular momentum. Okay? And after that, there are many experiments like there are many evidence. So when you observe the hydrogen's transition from n equal to n equal 1. So they are actually we expected a single line for this transition, but in the experiments we see the doublet, which means there are very closely spaced two lines. So this cannot be explained by the electronic structure just by considering the orbiters. And actually in 1925, you know his name very well, the Wolfgang Pauli. The Pauli that is the Pauli's exclusion principle. So he showed that all these observations could be explained with the postulate that an electron exists in two distinct states. So he introduced the fourth quantum number, the spin quantum number, called the spin m sub s. And this value is restricted to two values. So this value can only be plus 1 over 2 and minus 1 over 2. So far we just assume and we say that we introduced, right? So it doesn't really appear naturally. So some of you may feel uncomfortable because can we really see that? Is it does the spin really exist in the nature? So some of you might ask like that. And actually, yes. In 1930s, so Paul Dirac, another Nobel Prize winners. So he developed relativistic quantum mechanics. So he introduced, he combined the relativity, so Einstein's relativity and quantum mechanics. And in his equation, the Dirac's equation, the spin arises naturally. So if you solve his equation, then you will have the like 4-component vector. So your answer is no more single wave function. Value is consisting of 4 value, and this is like large value and small value and upspin and downspin, something like this. So spin naturally arises by solving the Dirac's equation. So this is very difficult subject, and my PhD advisor asked me to study this one, but actually I gave up. So I have nothing much to say about this one. So, but if you are interested in this one, then yeah, please go ahead. This is quite a straightforward way. If you want to win the Nobel Prize, then you have to study something like this one. Okay, so let's summarize the effect of the spin operators. So it is very similar to the eigenvalue equations for total angular momentum, L square and Lg. So let's try to recall. So total angular momentum is h bar square L plus 1 and Lg So similarly, S square for I might forget to mention. So we are going to indicate or designate the m sub s equal to plus half is alpha spin. Maybe you don't need a bracket notation, just alpha spin, and minus 1 with minus half is the beta spin. So S square of the alpha spin is equal to h bar s plus 1 alpha, and here s is equal to 1 over 2 half, and s square of beta is equal h bar square s G alpha is, so it's exactly m sub s h bar alpha. So s value is 1 over 2. So this is like the absolute value for alpha and beta. But m sub s is plus 1 half for alpha spin and minus 1 half for beta spin. So you can complete these relations. So I think we have to stop here. So that's it for today.